So, any questions from potential flow?
Yes.
Yes.
So for the sink and the source, the complex function, and we get because it's a log, so we do a series expansion, right? And finally we after we do the expansion, we're going to calculate the velocity. We only take the first 10 of the polynomial series. So I just wonder what's the physical effect of the other terms.
Again, I need to look at that.
So page 13.
In Bird-Stewart and Lightfoot, you'll find potential flow examples and tripping flow and boundary layer all done in chapter 4, but in a very quick, he just gives you the quick overview of it. So I took a lot of this material from other books, but I think I have pointed out one is the book by Kundu, and the other good book in this particular potential flow would be a book by Curry, mechanical engineer. Okay, so I go to 13.
Yes. Yes, here.
Right.
So we calculate the capital F. We just take the first term and we get a n epsilon over pi j. Then
Right.
we take this complex function to calculate the velocity field for
Right.
that gives me kind of a circular.
For the source and the sink, right?
Yes.
Right. Yeah. Epsilon here is a parameter, and okay, so this function f equals m over 2 pi log z minus a gives you either the source or the sink, depending on the value of m, positive or negative. Okay, and the location of the sink is at a. Now, a doublet is both a source and a sink. That is, one of them acts as a source, the other one acts as a sink. So when you have a source, you, like in this case, this is the source from which the liquid comes, and then it goes radially in all directions. That's a source. If you change the arrow direction, it's going to be a sink. Okay, and that is captured by this function that you see here. But a doublet is one that has I guess there is a figure somewhere here. Okay, so it is both a source and a sink. Okay, so from this side, for example, it enters in there. So from this side, it's a sink. From here, it's a source. And the way you construct that is by placing either a source or the sink, for which we have an analytical result, which is log z minus a, at points that are close enough to each other. So the source and the sink are only a slight epsilon away from each other. So epsilon is a very small distance, and you let epsilon goes to 0. So the source and the sink basically merge with each other. Okay, and that's when you get this kind of a potential lines. And in that case, epsilon is a parameter which indicates the distance between the source and the sink. And that parameter is a small parameter. So you can neglect the higher order terms. And that will capture the doublet, which would be the source and the sink, the combined effect of the source and the sink. Now, if you have finite value of separation, then epsilon will be finite, and you need to take more terms in the series.
If we take more terms, where you ask the same?
No, you will have, actually in this figure, they are almost merged, so there is only one point. So they will move away. That epsilon is the distance between the source and the sink. So the source and the sink will move farther and farther away. Okay. And in fact, in petroleum engineering literature, you'll find this used a lot, because a source would be the production valve and the sink will be an injection valve. And when you're modeling the reservoir on a large scale, they are governed by something called Darcy's law. If there is time, we will look at that. And you can convert that into a potential flow-like equation. And there's a whole book by Baer on flow through porous media, which talks about potential flow solution approaches to porous media flows, where these sources and sinks are used, not necessarily close to each other forming a doublet, but distributed at different locations. Now, the nice thing about the potential flow solution is, because it is linear, the equations are linear, if you have different sources and sinks, you can superpose them, you can add the solutions, you can add the functions to get the net effect of the flow field when you have multiple sources and sinks that are farther away. Because you know for each one you can add them up. Okay, so this is just a mathematical series expansion that you truncated, and the physical reasoning is that in a doublet that the two sources and sinks are very close to each other, so epsilon is small. Okay, so I'm glad that you're looking at things that I asked you to look at. All of you, it is very important by the time you get to the final exam that you go through any additional reading material that I give. And the other thing that I was just thinking about is, if you remember, I have 5% for class participation, and so I might give a quiz next week, either Tuesday or Thursday, for about 15-20 minutes, and basically to check whether you are getting the concepts. Okay, whether you're putting, because we are really covering a lot of material and I'm going fast. I'm able to go fast because I have the pre-prepared notes, but I'm not sure whether it is helping or hindering your learning. I don't have any feedback on that. The assignments serve a different purpose. The assignments you need to actually work out in detail, go through the various steps, and there is some aspects that I expect you to learn on your own, like in the current one on ComSol for a sphere and a cylinder. Okay, but there are lots of concepts that we have been talking about: the similarity transformations, the lack of length scale in potential flow, the condition of irrotationality. So there are a lot of little concepts like that, and unless you kind of read and follow it up, it's not, by just listening to it, I don't think you will retain a lot. So next week, expect a quiz, either Tuesday or Thursday. Any other questions or comments? All right, so quickly reviewing what we saw in the last lecture is this Cauchy-Riemann condition satisfied by this stream function and the velocity potential, that is d psi dx2 equals d phi dx1, and d phi dx2 is minus d psi dx1. And they both give you the velocity field. So there are two ways of getting at the velocity field, either by solving a Laplace equation for the potential or a Laplace equation for the stream function. If you do that, you will automatically satisfy the continuity and the Euler equation. And we saw that these conditions are automatically satisfied by any complex function, analytic function. And so if you take a function and separate it into its real and imaginary part, you get a phi and a psi for some potential flow problem. And when I say some, we don't know for what geometry it could be a solution. So the problem is reversed. I have the solution, and then I'm asking, okay, what is the geometry for which it could represent a solution? Instead of what we did for creeping flow, where we're given a geometry, and then we solve the Stokes equation for that particular geometry. And the other thing we saw is that if you take that f and take its derivative with respect to z, that gives you the complex velocity. And if you split that into real and imaginary part, you get v1 and v2 directly. But you can also take the phi and psi and put it into the equation and get the velocities. They will give you identical result. And from that expression for Wz, if you factor out an e to the power minus Iz, then whatever is left, you can interpret that as the velocity in the radial coordinate and the velocity in the angular Cartesian, cylindrical frame in radial and angular directions. And another important, these are the concepts I'm talking about in a quiz. Like we saw that every solution to the potential irrotational flow is also a solution to the Navier-Stokes equation. Then why is it that we are not getting the full solution? Why is the potential flow solution not a complete solution to the Navier-Stokes equation? And the resolution for that is in the no-slip condition. Similarly, what is Stokes paradox? What is D'Alembert's paradox? And things like that. What is the concept behind the Austen equation? You should be able to express that in a few sentences with maybe an equation or so in a quiz. Now, the boundary layer theory is a theory which is developed by Prandtl in 1904, an elegant theory that brings together it is a midway resolution between potential flow and creeping flow. Creeping flow is valid for low Reynolds number, potential flow is valid for very high Reynolds number under idealized condition. So in each case, what we did was we threw out one term. When we looked at Stokes equation, we said inertia is not important, we throw that out. When we looked at Euler equation, we said viscosity is not important, we throw that out. And so from Navier-Stokes equation, we get Stokes and we get Euler. And now we are getting something called the Prandtl boundary layer equation. Again, the idea behind this is very important. The math is fairly tedious in terms of going through the steps, and I will go through it quickly, but I want you to spend the time to fill in the gaps. But the basic idea is what we need to understand. What is a boundary layer concept? What is a boundary layer concept in fluid mechanics and in other areas? In fluid mechanics, it is the following. If I have a thin plate, you can think of it as a wall or a floor or a ceiling or whatever, and I'm blowing air, for example, past that. So I have fluid that is approaching that. So, and the plate starts here. Okay. So if it were a potential flow, if the fluid had zero viscosity, the fluid will not even notice the presence of the plate. It will just slide past it. But because the plate, the fluid is real and have a finite viscosity, the velocity near the plate must be zero, no slip condition. It sticks to that. Okay. But if you go far away from the plate, the velocity will be close to your free stream velocity, the approach velocity. So there is a thin layer that develops, and that is called the boundary layer. Conceptually, that is called the boundary layer. And inside the boundary layer, if you plot the velocity profile will look like this. Okay. If you plot it at different locations, the velocity profile is going to look like that. So this is the velocity vector. But as you go outside of the boundary layer, if you extend this, the velocity will be constant at the value of u. Okay, this is for a flat plate. Of course, we can then generalize it for curved shapes, etc. But we are going to look at mostly flat boundary layer over a flat plate. So the idea that Prandtl came up with is that there is a very thin layer close to the plate where viscosity is important, viscous effects are important, and you cannot assume the viscosity to be equal to zero. So you must solve the Navier-Stokes equation in that region. Outside of that, you can throw the viscosity effects away, and you can assume that the potential flow solution is a good solution. Okay, so inside that region, we need to now do a very careful analysis so that we don't end up throwing completely the viscous term or completely the inertial term. We need to do a finer balance between the viscous and inertial term, and that was his main contribution. He did not even solve it. He could not solve it. In 1904, there were no computers, right? So it had to wait for another 30 years. In 1930 or so, Blasius came and developed a solution to that. So what Prandtl's contribution was, propose this idea of a bound layer and write down the equations from the Navier-Stokes equation, and this is called the Prandtl boundary layer equation. And we're going to go through the process of how he developed that using very careful scaling arguments. Okay, but let's look at a simplified version of um, an ordinary differential equation, and this is a model for a spring and a dashpot. Okay, so what it is you have a spring and something called a dashpot. At the end of it, you have a mass m, and the spring has a spring constant k, and the spring has a spring constant c, and the dashpot has a constant k. You know what a dashpot is, right? It's basically what you see in the spring-loaded doors when they automatically close. Okay, so you have a spring that is loaded onto it. So when you open it, the spring stretches, and when you release it, it'll just bang back very quickly. Okay, but you don't want that to occur quickly. So what you put is you put a dashpot, which is a viscous material, so that it offers resistance to the motion, slowing it down. So this is basically, as you can think of it, as a kind of a cylinder with a viscous fluid inside. So it will dampen the return motion. Okay, so in this particular example, what I have is I have a wall, I have a solid object onto which I put a spring, and in series I put a dashpot to it, or in parallel. There are many models that you can do. Okay, and that is connected to a mass. And if you analyze the force balance on this, you will end up getting an equation like this. The problem is, what is the dynamics of this particular mass? If I have this mass and I pull that mass and release it, what is going to happen to that? I think I should actually have this. I have this incorrectly. It should be in parallel. Otherwise, I won't be able to explain this particular phenomenon. So let me write it in parallel. That's a mass. Okay, and the dashpot has a constant k, and the spring has a constant c. So the spring constant is a property of the spring. So the force is, what we are saying is the force exerted by the spring is proportional to the displacement. X here is the displacement of the mass measured from there, from its equilibrium position. So if it is in an equilibrium position and I come and push it or pull it, it wants to go back to that equilibrium position. Okay, and the spring will exert that force that takes it back to the equilibrium position. That will be proportional to Cx. The dashpot will resist that motion at a rate that's proportional to how fast the object is moving. Okay, and that is the rate of change, dx dt. And this proportionality constant is like viscosity. Okay, so, and these are the external forces. And what does the first term represent then? M times d square x dt square. That's the acceleration, mass times the acceleration. So there is nothing but application of Newton's law for a situation like this. There are a number of other examples where you will end up with an equation like this. In electrical engineering, the resistance, capacitance circuits, they can be described by equations of this type. So this equation occurs commonly in many situations. Okay. Now we are going to study the behavior of this particular equation to understand what we mean by a boundary layer, and then go to the Navier-Stokes equation and develop that concept for the Navier-Stokes equation. Now, do this thought experiment. Before we look at the analysis of the solution, do this thought experiment in your mind. I have two such devices, okay, mounted on the wall. Okay, the spring and the dashpot, and a steel ball that is attached to one of them. And on the next to it, on the side, I have another device, identical device. I have a styrofoam ball attached to it. Okay, and I pull both of them to the same distance and I release. What would you observe? What does your intuition tell you? Yeah? Start. They're going to reach their equilibrium position. And how would they reach back to their equilibrium position? They were in the equilibrium position, and I perturbed it. I pulled it, and I released it. And they want to go back to the equilibrium position. My question is, one is a styrofoam, the other one is very heavy steel ball. How will they approach that equilibrium position? Think of the steel ball. Okay.
Steel ball will go back first because it has more force. The mass is big.
Mass is big, yeah. So
It'll like having more force in the opposite direction.
the force is exerted by what? Not by the mass. It's by the spring. So if I have the same displacement, the force exerted by the spring on the styrofoam ball and on the steel ball is going to be the same. They will both be pulled back with the same force. Identical spring, identical dashpot, identical size spheres, the mass is the only difference. The answer is in the mass. Okay. So what were you saying?
If you look at the momentum, mass and velocity,
Right.
for the steel ball it will be higher, so the oscillations will be more.
That is the keyword I'm looking for. Okay, there will be oscillations. Okay, what would happen is as the steel ball returns to its equilibrium position, by the time it reaches the equilibrium position, its mass is big and it has a certain velocity. So it will overshoot. So it will compress the spring. And the spring doesn't want to do that, so it's going to push back. Right? So it will go back to its equilibrium position with a decaying oscillation. And we have to see whether this equation captures that phenomena. Whereas in the styrofoam, it doesn't have as much momentum, as much as inertia. So it will go back monotonically to its equilibrium position and stay there. Because by the time it reaches its equilibrium position, it doesn't have a lot of mass, so it doesn't have a lot of inertia. It's not going to overshoot. So one will give you a response that is oscillating, a decaying oscillation. The other one will give you a monotonic return to its equilibrium position. Okay? And can we capture these physical expectations from this particular differential equation is the question. Okay? So what is the solution? This is an ordinary differential equation, constant coefficients. M is a constant, K is a constant, C is a constant. So you should be able to solve this. You write the characteristic equation, and as long as this M is less than, much less than K square over 4C, the solution can be written like this. Okay, so there will be basically two characteristic roots or two eigenvalues, and these are minus C over K and minus K over M. Okay, one has M in it, the other one does not have M in it. So when M becomes large or small, the behavior of this term is going to be quite different. That's what we need to look at. Now, what we did in the Euler equation is we said viscosity is 0, so we threw that term away. So if we do the same thing, the styrofoam ball mass is very small, M is small. So can I throw this term completely because M is small? Then what kind of behavior would I get? Okay, that's the question that Prandtl started asking. Is there something fundamentally wrong in neglecting the highest order term? Here, M turns out to be multiplied by the highest order derivative, d square x dt square. So when you drop that, the character of the equation changes. It becomes first order all of a sudden instead of a second order. So instead of having two solutions, you will have only one solution. Okay, so there is a similarity. M going to 0 is similar to nu going to 0 in the Navier-Stokes equation. We lose the highest order term, and that gives rise to something called the singular behavior. And the argument is, even though M is small, d square x dt square is not small. Same thing in Navier-Stokes equation. Even though viscosity is small, the term that multiplies the viscosity, the del square V term, is not small. It is large in that boundary layer, in the small region. Outside of that, it's small, so you can neglect that. So potential flow will give you a correct result. But in that region, it is not. Okay, so that is the basic idea. So if I make the styrofoam analysis, I end up getting this equation, the first order equation, because I have thrown out the second order term. And when I get the solution, I get the solution as x equals a times e to the power minus ct over k. And that solution is the same as this part. But for this equation, I don't get the second solution because I've assumed M to be very small. If M is small, what happens to this term? 1 over M becomes very large. So minus e to the power minus a large number is going to be going to 0 very quickly. Okay, but it will not be identically 0 because you can, for any given value of m, you can always find a t over which that term is of order 1. For example, microsecond, if it is kilograms for a microsecond, that term would still be of order 1. So I cannot neglect that. But the region over which that term makes a contribution becomes smaller and smaller. And that region is what we call the boundary layer region. Any question? So we've been basically talking about the concept of what a boundary layer is, consequences of dropping the highest order term in a differential equation. So we have to, of course, evaluate the two constants, but in this case, we just evaluate one of the constants by saying at t equal to 0, x equal to 0 is the equilibrium position. When you do that, the full solution will become like this. Still one integration constant to be determined. That will depend on the initial velocity. Initial position and initial velocity must be specified because it's a second order equation. You need two conditions. But we'll just not worry about it because it's not central to our argument. But imposing this condition that x equal to 0 is your initial equilibrium condition, the solution becomes like this. Okay, so now we are going to compare the two parts. Okay, let me just sketch the solution for you because I don't think I have that. I've left the space. Okay, so if I plot the full solution, that is this solution, x versus t. T is the independent variable, x is the dependent variable. How does that solution look like? Okay, so it starts with 0. Okay, when t equal to 0, for example, you put t equal to 0 on both terms, you'll get 1 minus 1, which is 0, which satisfies the initial condition. Then as t increases, you will get a displacement like this, and then it comes down. Okay, this is for a certain value of m1. If you have a different value of m, it may be like this, m2. It may be like this for m3. Okay, and in all these cases, I don't have oscillations. Why don't I have oscillations? Because I've started my analysis with the assumption that m is less than k square over 4c. If m is greater than k square over 4c, what would happen? The solutions will have a complex quantity because the square root, you have to remember when you're solving this, you need to solve a quadratic equation. Okay, so the discriminant will be negative and you will get a e to the power it. That will give you cos t and I sin t. And that's what gives you the oscillations. So this condition, by imposing this condition, I'm looking only at styrofoam. I'm not looking at the steel because I'm making m to be smaller than the parameter k squared over 4c. So the only solution that I'm sketching here are for this function, not for the sine and cosine variation. And these solutions are going to look like this. Now, which one would correspond to the larger m? So you have m1, m2, m3. I guess I should label them in sequence. Okay, so let's call this m1, m2, and the third one is m3. Which one would be larger and which one would be smaller, do you think? Would m1 be the larger one or m3 be the larger one?
I'm sorry, largest. I'm sorry.
M3 is the largest of the set, right? Because as this becomes large, that term becomes negligible very quickly. Okay, so in this particular situation, M3 will be greater than M2, will be greater than M1. Now, if I plot the other solution that I have here, e to the power minus ct over k, that is exactly the same as the first part. Okay, and what I will find is for each case, I will find something like this. That solution cannot satisfy the initial condition x equal to 0 because I have only a first order equation. Okay, so this is what we would call an outer solution. The red line is given by a solution to this equation, which is equivalent to our Euler equation. Okay, and the Euler equation cannot satisfy the no-slip condition. In the same way, this solution cannot satisfy x equal to 0 at t equal to 0. So when you evaluate that term alone at t equal to 0, you will get some number. That solution becomes a good solution over large time. It agrees with the solution, complete solution over larger time. But there is a time region for each value of m up to which the total solution is completely different from the outer solution. So this would be called the outer solution, meaning the solution that is obtained for t going to infinity, larger values of t. Okay, and the solution that appears up to that value will be called the inner solution. This part is the inner solution. Solution for the inner region in the boundary layer context, or the solution near time t equal to 0. Okay, and there is a singular perturbation theory that will actually match these two solutions, and the method of matched asymptotic expansion was developed based on these ideas. But what we are going to do is look at only the boundary layer. So this is the idea of a boundary layer, that there is a small region close to t equal to 0 in this case, where the solution changes from 0 to the full value. From there, the outer solution is a good approximation. You can make that approximation, throw m term away, and get a solution that will be valid for large time scale. In numerical analysis, this is coined as a stiff differential equation. And this was analyzed in the 60s, again by chemical engineers, looking at chemical kinetics. If you have, for example, 2 or 3 reactions, one reaction is very slow, the other reaction is very fast. There are different time scales, and then you end up with a response like this, where the equations have very wide separation and eigenvalues. Remember, these are the eigenvalues, k over m and c over k are the two eigenvalues, lambda 1 and lambda 2. And if m goes to very small, these eigenvalues can have very different magnitudes. And that is an indication of what are called stiff differential equations, with a very sharp response over a short time scale, and then slow response over a larger time scale. That idea of boundary layer theory was developed in 1904, but the concept of a stiff differential equation came about in much later, in the 60s. A lot of algorithms were developed for handling those. And in reactor course you will do in the next term, you'll revisit the same idea from a different angle. This is called quasi-steady state approximation. So when you have multiple reactions, if one reaction is going fast, you say, okay, that's going to reach equilibrium. So that equation is going to be, that reaction is going to be always under equilibrium condition. Then the slow reaction is the one that determines the dynamics. So that's called quasi-steady state approximation. Quasi meaning in one part is steady state, the other part is not. And all these ideas are kind of related, the same root in terms of a mathematical concept. Any questions? Is the concept clear? What is a boundary layer theory? So let's go through and fill this table. Okay. So here we looked at an ordinary differential equation. Now I want to compare this with what appears in the Navier-Stokes equation. Okay. So m in this current model is equivalent to nu viscosity in the Navier-Stokes equation. The complete equation 1 is equivalent to the full Navier-Stokes equation. The simplified equation 3, where we said m is 0 and we threw out the second order term, is equivalent to our Euler equation. You should understand the reason why we cannot do that. Even though m is small, the derivative term that multiplies is large. So the product is still of the same order of magnitude as the other terms. You cannot simply throw that out. Okay? That's what calls for a very careful balancing of various terms in a differential equation. And that was the main contribution of Prandtl. The initial condition is equivalent to the no-slip condition. The slowly varying solution, the red line that I indicated, the outer solution is equivalent to the potential flow solution. Okay, because it cannot satisfy the no-slip condition. If you look at the outer solution, it just has some starting value at t equal to 0. Okay, and the last one, the fast varying solution, that is fast response over a very short time, is what is our focus currently. It's called the boundary layer. So what we need to do at this stage is do a very careful balancing of the various terms, because we know that we get into two different difficulties. If I throw the viscous term, I get potential flow equation, which cannot satisfy no slip. If I throw the inertial term, I get the Stokes equation, which is not valid beyond a Reynolds number of 1 at the most. Okay, so I need to bridge these two, and the boundary layer theory does that. So this is a sketch of a boundary layer, not around a flat plate, but something like an airplane wing, for example. So this would be the boundary layer that you are seeing, the dashed line. Now, such an object, the shape of the object here is in the form of a symmetric airplane wing. Okay, you can solve for that from potential flow equation to get the velocity field. And that velocity field will not be uniform, and that velocity field will be the potential flow solution, u of x. So it's going to be a function of x. For a flat plate, that u is a constant, okay, which we saw from potential flow theory. But for any other object, like for cylinder, for example, there is a potential flow solution. And if you take a cylinder, for example, the potential flow solution that you get will be valid far away from the stream, but near the solid you will have a boundary layer like that that's growing very thin, and you might have a boundary layer separation when there is a wake, for example. But these objects are designed, the airplane wings are designed in such a way that you don't have a wake, because wake results in significant drag, significant loss of energy. Okay, so we're now ready for doing a proper scale analysis. This is my geometry, a flat plate, and these are my coordinate systems, x1 and x2. The proposition for the velocity field is that it is going to depend on v1 and v2, and they're both functions of x1 and x2. So I'm looking at two-dimensional boundary layers. Of course, there is obviously three-dimensional boundary layer as well, but we are looking at only two-dimensional flows. So perpendicular to the board, everything is invariant, nothing changes. But the velocity changes in the x1 and x2 direction, and that is your boundary layer. Now the boundary layer is only a concept. There is no sharp line that you can identify as a boundary layer. But when you plot the velocity field will look like that. So we can define arbitrarily the thickness of the boundary layer as that thickness at which this velocity reaches that 99%, for example, of the free stream velocity, or 95% of the free stream velocity, the potential flow velocity. Okay, so there is certain arbitrariness. So in that sense, this boundary layer thickness is defined only in an asymptotic sense. As you go far away from the plate, the velocity approaches that of the potential flow velocity. Let me ask you an intuitive question. Okay, I have two fluids. One is a syrup, the other one is water. They are both flowing over two plates. Which one do you think will have a thicker boundary layer from what we have discussed about boundary layers? The more viscous one will have a thicker boundary layer. That's good. So your intuition is really tuned in the right direction. Okay. So the thinner the viscosity, the smaller the boundary layer. Qualitatively, we know the direction. What we want to do is quantitatively get that information. How does it vary? Does it vary as linearly or quadratically or square root? What is that relationship? So that we can get without even solving. That is the amazing thing. Prandtl was able to do this without solving the differential equation, because he couldn't solve these partial differential equations. He was able to get that relationship by simply doing an order of magnitude analysis. So under this assumption of V1 and V2 are non-zero, they depend on x1 and x2, I can simplify my continuity equation and the two momentum equations. So I have three unknowns. These are V1, V2, and P. V1, V2, and P. And I have three equations. Incompressible Newtonian fluid. Okay? And the key in Prandtl's ingenuity is the following. I have the plate. So the plate has a finite length, right, in the x1 direction. But in the x2 direction, this boundary layer thickness, I don't have a natural scale. I don't know what it is. But I know that it is thin. And it is proportional to, in some way, proportional to the kinematic viscosity. The larger the viscosity, the thicker the boundary layer. So he said, I don't know what the characteristic length I should use. Now, what we did, if you recall, when we did the scale analysis for creeping flow, we introduced the same scale in every term. We use the same velocity scale for same length scale in every term. But he said, no, I cannot do that. So the velocity changes in the x1 direction over a length scale of L. But in the x2 direction, it changes over a length scale of delta. But I don't know what delta is. I know what L is. I don't know what delta is. I need to find that out. So he built himself some degrees of freedom. So he introduces a scale which is unknown, but it gives him the degree of freedom to balance the two terms. If I don't do that, I will come to the conclusion that either the viscous term is dominant or the initial term is dominant. In this case, both are important. Okay? And that was the first thing that we introduced, recognized the need for a length scale in the x2 direction, and we call it delta and treat it as an unknown. Similarly, the velocity in the x1 direction is u. Okay? It is approaching with a free stream velocity of u. I know that. I control that. But would there be, let me ask you this question, would there be a velocity in the x2 direction? The flow is approaching it with only one component. In this flow, there is no x2 component. It's approaching with u. Hits the plate, and we say it develops a boundary layer. And inside the boundary layer, if you plot the x1 velocity component, that velocity component is something like this. But will there be an x2 velocity component?
I don't know whether I'm right, but there will be, but it will be very negligible compared to the horizontal.
You're absolutely right. Why?
The flow rate in the x1 direction is decreasing.
Very good. So the net flow in the x1 direction will decrease. The moment it hits a plate, okay, if you calculate the flow rate here, this will be based on u times that thickness. But if you calculate the flow rate in this region, it's going to be somewhere lower than that. Why? Because the velocity here is 0. The velocity here is u. So the average velocity must be somewhere between 0 and u, right? And that means it looks as if the material has disappeared. It cannot. Conservation of mass dictates that it must be there. So it says, okay, I'm going to deflect a little bit upwards. Okay, so whatever comes in minus what goes out must equal to what comes out of this. And that is enforced by the local continuity equation. Because this equation immediately creates a dv1 dx1, which I know is not equal to 0. Okay, that means dv2 dx2 can also not be equal to 0, but they must add up in such a way that the sum is equal to 0. You can see that as the source of generating the vertical component v2. So v2 is going to be present, and it is created by the requirement of a continuity equation. So, and under this assumption, we simplify the x1 momentum equation, which is given by 2, and the x2 momentum equation, which is given by this. So it's a complicated nonlinear differential equation, but as you said, the velocity component in the x2 direction is going to be small, okay, because it changes over a small distance of delta. So he introduced an idea of a different velocity scale v. Again, I don't know that. It's an unknown. But I know that v has to be much smaller than u. Okay, that's all I know. Okay, and then he introduced a scale for pressure, pi, and we will see what pi is. Pi, you can write it as rho u square if you want, but it's some unknown scale. So the main generalization here is that I can introduce scales as unknown factors so that I have the degrees of freedom to play with matching the various terms and discover what these scales must be. Okay, so in the process, I will discover what delta is, how big delta is, magnitude-wise, not the exact value, but magnitude-wise. That's a new part that we are introducing, that we can recognize the scales are different in different directions, so we must introduce different scales. They may be unknowns that we will try to find out. The rest is routine mathematics. Okay, so once we have introduced these scales, v1 bar is the dimensionless velocity, which is v1 over u. Okay, and v2 bar is v2 over v, not u but v. So that, why do we do that? What will be the range for v1 now? v1 can go from 0 to 1. Okay, similarly v2 will go from 0 to 1. v2 is also 0 at the plate, the impenetrability condition. But it will go to maximum v at the outside. So we don't know what it is. Okay, so but we are scaling everything so that they go between 0 and 1. So we can treat all these terms as of order 1. Similarly, x goes from 0 to L, but x2 goes from 0 to delta. They are two different scales, and p is scaled with respect to pi. Okay, this is standard definition of how we would define dimensionless variables, but the key is to recognize that we have introduced unknown scales. V is unknown, delta is unknown, pi is unknown. But we are going to balance them and find out what they are. Okay, any questions? Okay, the next step is take these definitions and put them into the original equation and factor out these scale factors. That we have done many times, so I can go through that very quickly. So what have I done here? I've just used the definition for V1 in terms of V1 bar times U. So I get the U out here. Similarly, X1 bar is X1 times L. Okay, so, sorry, X1 equals X1 bar times L. So the L comes out of here. Similarly, from the second equation, I get V over delta because those are different scales. Previously, I would have used the same scale. I would get U over L. I would say, okay, U over L just drops out. But here, I have pointed out that these things are scaled between 0 and 1. Okay, so this derivative now hopefully will scale between 0 and 1. This will be of order 1. So it is this term that I don't know. But if I argue, for example, that U delta over V over L is much smaller than 1, what can I conclude? If this term is much smaller than 1, remember, this is of order 1, this is of order 1. So if this is much smaller than 1, this whole term is going to be negligible. So I need to impose dv2 dx2 equal to 0. Right? The equation simplifies to this. This implies that v2 is not a function of x2. v2 is a function only of x1. Right? But v2 is 0 at the entrance. So what does that tell you? This is a careful logic that you need to follow. Okay? If this is small, the consequence of this is dv2 dx2 from the continuity equation must be 0. If that is 0, then v2 cannot be a function of x2. v2 must be a function of x1. So v2 can change only with x1. Okay? But v2 is 0 at the entrance. So it must be 0 for all, because you can evaluate what the condition is. So it must be 0 for all x1. That leads to a contradiction. Then you examine the other condition. What happens if this is too large? This is too small, this is too large. If this is too large, then this is the dominant term. I can neglect that. And if this is the dominant term, then I will get dv1 dx1 equal to 0, which implies v1 is not a function of x1. Okay, and that implies that v1 is a function only of x2. But v1 is equal to 0 at the wall. Okay, so for all x2, it must be equal to 0. Okay, so either one leads to a contradiction. So we say that it is neither small nor large. It is of order 1. That entire term, u delta divided by VL, is of order 1. Okay, so this is now trying to estimate what is delta and what is V. If we can develop 3 such conditions, we can solve for those equations and say what is the order of delta, what is the order of V, what is the order of pi. So we're not solving an equation, we are solving an order of magnitude estimate of these terms. Any questions on that? And that is what we call a very careful balancing of both terms. Both terms are equally important when I make this term of order 1. So my continuity equation then simplifies. The dimensionless form of the continuity equation simplifies to dv1 bar dx1 bar plus dv2 bar dx2 bar equal to 0. Next, we go through the same idea for the x1 momentum equation. Okay, this is going to be a bit more complicated because from v1 you have another v1. So there are two v1. So what will I get out of that? v1 is scaled with respect to u. So I get u square. I already have rho there. And in the denominator, I have x1. So I get L from that. Okay. So this whole term has become dimensionless, meaning it is of order 1. But I don't know what this term is. Okay. So I just group that term as such. I do that for every one of the equations in the x1 momentum equation. So from here, I get v2, which gives me v, v1, which gives me u, and x2, which gives me delta as a factor when you put them in dimensionless form. Okay, and similarly from here, x1 will give me L, and p will give me pi. Are you following me? So v1 will give me u. The mu already exists in that term, and x1 square will give me L square. Okay, and similarly here, x2 square will give me delta square, and v1 will give me u. So I have obtained the pre-multiplying factor in every one of those terms in the x1 momentum equation. In the process, I made the dimensionless terms of all order 1. So now I need to balance this. Well, how big is this compared to this, compared to this, compared to that? So I need to make an order of magnitude estimate. Okay? Any questions on that? Okay. You see, this is where, because I've written it down, I can go fast. And by looking at it, you say, okay, I follow it. And then the test that you should apply to yourself is take a piece of paper and see whether you can develop that. Okay? Because you can understand it, but that's different from actually doing it. And you need to develop that skill by the time you go to the final exam. Okay? So, the next step is to manipulate these factors, pre-multiplying factors, in such a way I put them in dimensionless groups. All I know so far is that these terms, the derivative terms, are all dimensionless. But the pre-multiplying terms have a dimension to that. Okay? So I realize that from the first equation that I have here, u over L is the same as v over delta. U over L is of the same order as v over delta. That's a key thing to understand. U is large, L is large, but the ratio is the same magnitude as v over delta. V is small and delta is small, but the ratio is the same as the ratio of two large numbers. This is the ratio of two large numbers, this is the ratio of two small numbers, but still they are of the same magnitude. Okay? So we can use that fact, and wherever I have u over L, I can replace it by v over delta, I replace it by u over L. For example, here I have a v over delta. I've replaced it by u over L. Okay? And I just leave this as rho u square over L, and pi over L remains the same. And in here I factor mu u over delta square out. So in order to do that, I need to multiply the first term by delta square over L square, and the second term remains as it is. Now let me ask you a question. Between these two terms, which one do you think is important? In the viscous term, between this term and this term, the viscous diffusion in the x1 direction, the viscous diffusion in the x2 direction. After we have done this manipulation, we should immediately be able to tell that this term is going to be maybe small. Why? Because I know delta is much smaller than L. So delta square and L square is going to be even smaller. Okay? So I can neglect this term in relation to the next term in the viscous term. okay, compared to those two. But the remaining terms I cannot tell. I need to figure out what is going to happen. So the next thing I do is I multiply every term by delta square over mu u, which is this term, the inverse of that. Why would I do that? That will make this pre-multiplier of order 1. Okay? And when I do that manipulation, I get delta square. I mean, this is, I'm just showing you that every term I multiply by delta square over mu u. And then this becomes rho u delta square over mu L. Both the initial terms. There are two initial terms here. Both of them have the same factor, rho u delta square over mu L. And here I have another factor. Now comes the logic, the argument. Okay, so if I argue, for example, that this is too small, this term is too small, what would that lead to? I'm throwing out the initial terms. I'm going back to my Stokes equation because these are the initial terms. If you argue this is too large, then I'm going to the Euler equation, potential equation. So this must be of order 1. That means I must balance the inertial term against the viscous term and against the pressure term. So I must make this also of order 1. Okay? I must make this of order 1. I must make this of order 1. Remember, when I started this, I introduced 3 unknown scales, delta, v, and pi. So by insisting in the continuity equation that u over L times delta over v must be of order 1, I've used up one of those degrees of freedom. The 3 degrees of freedom, I've used up 1. I'm using up the remaining 2, insisting that this be of order 1 and that be of order 1. Okay? And that's what I'm showing here. Rho u delta square over mu L must be of order 1. That can be rearranged by writing as delta over L must be equal to square root of nu over Lu, or which is the same as 1 over square root of Reynolds number. So your intuition told you that the boundary layer thickness should increase when the kinematic viscosity increases, but we couldn't tell whether it is linear or quadratic or cubic. Now what does this tell you? It varies as square root of nu. Okay, the boundary layer thickness varies as square root of nu without ever solving what the differential equation is. Okay, and then when you impose this condition that pi over L delta square over u mu should be of order 1, you will get pi as equal to rho u squared. So we have solved for all 3 scales. Okay, v over delta is equal to u over L, known scales. U over L is a known scale. Okay, and then delta over L is equal to 1 over square root of Reynolds number based on the length. The Reynolds number needs a length scale. The length scale here is the length of the plate L. Okay, and then pi is equal to rho u squared. So we have found out all the 3 scales in such a way that the continuity equation has both the terms and the momentum equation, x1 momentum equation has the inertial term, only one of the viscous terms. The reason the other viscous term is out is because delta square over L square is small. Question?
Can you explain that last one? The pi is equal to rho u squared?
Yeah.
How do you get to that?
I get that by insisting that this pressure term must be of order 1. If I say if it's small or large, I lose the pressure term. So the pressure term is of the same order of magnitude as the viscous term, which is the same order of magnitude as the emission term. So I impose this condition, pi over L delta square over mu u must be of order 1. Okay, that means mu u L over the pi, that is take pi to the other side. Okay, so pi is equal to mu u L over delta square, because this is of order 1. Right? So when I say, I'm treating this as an equation, but replacing it with the equal sign with an order sign. Okay? So I can still move this to the right hand side. So mu L u over delta square is pi. Okay, but then I use the fact that delta from here is substituted there, delta square, and that's how this was simplified to rho u square. That's the step I guess I didn't explicitly write it out. So you should use the delta, because delta is given in terms of all known numbers here. So take this to the right hand side and square it, delta square, so you'll get mu over LU L squared. So you get L is equal to that.
Excuse me.
Yeah.
Why you said the pressure term cannot be dropped?
That's a good question. Is it intuitively obvious why the pressure term must be there? And it turns out that it's not intuitively obvious. You need to know something about when a pressure gradient will exist even in a potential flow. For example, in a flat plate, there is no pressure gradient for potential flow because it's uniform flow. You don't need a pressure gradient to apply to keep the fluid moving because zero viscosity. But if I have a potential flow past a sphere or a cylinder, which we saw, that there is a pressure gradient as you approach that in the x1, x2 coordinates, for example, P will be a function of both x1 and x2. So there will be a gradient that develops even in the potential flow that balances against the inertial term in the Euler equation. Okay, so we cannot say that it is zero. We cannot drop that. So that argument tells you that this number is not small. Okay. The other argument is if it is large, then that's the only term that's dominant because we have made the other terms small of order 1. So if this is dominant, then dp dx1 is going to be equal to 0. Right? And that means the pressure everywhere is constant. That is also not true. So that must be balanced against the inertia and the viscous term in general. For flat plate, it turns out, and we will show, that this term in fact drops out to 0. For flat plate, there is no pressure gradient. That's why I said it's not intuitive. Intuition says it must be 0 for a flat plate. But, and it does indeed come out to be 0 for a flat plate analytically. That's a good observation. Yeah. Any other questions? Okay. Now we still have the x2 momentum equation left. We have taken care of the continuity equation, we have taken care of the x1 momentum equation, but the x2 momentum equation is there, but we have no more degrees of freedom. We have exhausted all the 3 degrees of freedom to balance the terms. So we don't have any ability to balance the terms here. And this is where Pratchell's ingenuity really comes. How did he just wrote down these equations. If you see the original paper, you won't have this elaborate explanation or justification. But this term he threw this out. This entire momentum equation is irrelevant. But what does this capture? It captures the momentum in the momentum transfer in the x2 direction. But we know that the velocity already in the x2 direction is small. The boundary layer thickness is small. Okay, so intuitively maybe expected that the x2 momentum equation is not going to be that important. But the scale analysis tells you that it is consistent, that you can throw everything out. Okay, so, but our starting point is the x2 momentum equation in dimensional form with rho and mu in there. And you go through exactly the same process. Introduce the dimensionless variable v1 and v2, that gives you u and v, and introduce x1, that gives you L. And here you introduce v2 and v2, that gives you v square, and x2, that gives you delta. Same process, okay? And then p gives you pi, and x2 gives you delta, and here v2 gives you v, and x1 square gives you L square, and v2 gives you v, and x2 gives you delta square. But you don't have any degrees of freedom. You cannot balance any of them. What you have to do is use already the factors that you have found, that pi is equal to rho u square and v is equal to u delta over L. Substitute that, okay? And I want you to go through this step, and what you will find is that every term gets multiplied by this factor, rho u square delta, and on the right hand side every term will get multiplied by mu u delta or L delta square or L cube. Okay, and to get rid of the dimensionless groups, multiply everything by L square over rho u square delta, and what you get in the final analysis is this equation. We have not made this by order 1. It automatically cancels out. When I make the substitution, there is no dimensionless group multiplying this. This is of order 1. Okay? This is of order L square over delta square, and this is of order delta square over L square. Yeah, delta 2.4 and delta 4 delta square over L square. Okay. So this is the final equation without trying to balance any of the terms because we don't have the ability to balance any of those terms. But we know that delta square over L square is much small. That is, delta is much less than L. The boundary layer thickness is less than the plate length. So every term gets multiplied by a small number. Okay, this term gets multiplied by a small number, that term and that term. So all you get from the x2 momentum equation is that dp dx2 is equal to 0. Okay, and that leads to the fact that p cannot be a function of x2. P can be a function only of x1. What does that mean? In the case of a flat plate, if this is x1, p can be different in various positions, but there cannot be any pressure variation in the x2 direction. Okay, and that tells us I can take the pressure distribution at the edge of the boundary layer and feed that into the first equation, because the first equation I still need dp dx1 in the general case. For flat plate, as I said, it turns out to be 0, but in the general case I still need that. Okay, and I get that as a solution obtained from the potential flow solution at the edge of the boundary layer, and that is consistent with this equation, which says P is a function of x1 but not of x2. So it is the same. If I take the pressure here, it's going to be the same everywhere. Now, is that consistent? It is consistent to the order of the approximation that we make. The approximation that we make is the thickness of the boundary layer is small. V is small. Delta is small. Okay, but you must realize that if there is a V component, there must also be a dp dx2 component. Okay, it's small. That's all we're saying, that the dp dx2 is small. It's not exactly 0 because none of these terms are exactly 0, but they are all small. That means dp dx2, because dp dx2 is the sum of all these terms. If these terms are small, dp dx2 must be small. Okay, so that's the development of the boundary layer equation. So in summary, the boundary layer equation is simply this. This is the equation that Prandtl wrote down in his paper. For a flat plate, dv1 dx1 plus dv dx2 equal to 0. And then in the second equation, you get the inertial term and only one component of the viscous term, d square v1 dx2 square. The other one dropped out from the scale analysis. What does this tell us? Physical interpretation now. The mathematics and the very fine art of balancing led us from the Navier-Stokes equation to this, which is called the Prandtl boundary layer equation. Is it linear or nonlinear? It's highly nonlinear. Why? The unknowns are v1, v2, and we have products of v1 here, products of v1 and v2 there. Okay, that is the nonlinear term. That is the term in the Navier-Stokes equation that still people haven't cracked. There is $1 million prize if we can show the existence of solution to this Navier-Stokes equation. We still don't know whether the solution exists or not mathematically, from a mathematical point of view. Okay, but the equation is derived from Newton's law of motion, and every test that we have done, measurements against prediction, analytically or computationally, agrees very well. Okay, so in that sense, there is no doubt that solutions exist, but mathematicians want to prove that it exists, and such a proof doesn't exist till today. Okay, and for the pressure, how do we get the pressure? We have only 2 equations now, and we have 3 unknowns still, v1, v2, and p. We get the pressure from the Bernoulli equation, p plus 1/2 rho u square equal to constant. So what pressure is this? There is no g in that equation. That is a dynamic pressure. Okay, and you can take the derivative of that to get you a dp dx1. So if you take the derivative of that, you'll get dp dx1 equals minus rho u du dx1. What is u? U is the potential flow solution outside of the boundary layer. It is the velocity with which it approaches the object. We did that for a flat plate, but the same theory works for shapes that have aerofoil or even blunt objects. You need to worry about proper coordinate systems. So this gives you the pressure gradient that you feed into that equation from the boundary layer. This is that merging, this is the marriage between the potential flow and the boundary layer. Okay, so the potential flow solution forces the pressure gradient onto the boundary layer equation. So these are known from potential flow. Now it turns out for a flat plate, what is du dx1? U is a constant, so du dx1 is 0. So for a flat plate, the pressure gradient is 0. So that is the general momentum equation. Now let's look at the flat plate solution. As I said, almost 30 years passed between the equations were developed and the solution strategy was developed for this. And the solution strategy was developed by converting the partial differential equation into a set of a single ordinary differential equation by Blasius. So it's called the Blasius solution. Now, yeah, before that I was going to talk about this. I was going to ask you, give me a physical interpretation of the left-hand side. Of course, pressure is pressure, and the right-hand side.
What was the question?
Give me a physical interpretation for the meaning of each one of those terms. That's a kind of quiz type of question. Okay. What does the left-hand side term physically represent? It represents the inertia. It represents the advection term. It's sometimes called the advection term or the convection term. It's a convection of the momentum. Momentum in what direction? Rho times V1. The x1 momentum equation that is being convected with the velocity of V1 d dx1, V2 d dx2. So that operator is the operator that says that something is being convected. Okay, so the left-hand side term is the inertia term or the convection of momentum term. And what is this term? In the x1 direction. This is in the x1 direction. What is that one? Diffusion in what direction? Diffusion of x1 momentum in the x2 direction. Okay, so this is what viscosity does. If I apply a brake to the fluid that is coming in by the wall, that effect is propagated in the x2 direction, right? By viscous interaction. What is the problem that comes to your mind when you look at this? A problem that we have seen before. I can ask a lot of questions now. You know where. That is the problem of Stokes solution for an impulsively started plate. So we studied this infinitely long plate and infinitely long fluid, and we impulsively start the plate into motion, and the fluid layer above that starts moving, right? And there is an analogy between this problem, boundary layer problem, and that problem. I want to see whether you can explore that analogy. Okay, for a flat plate, this term is 0. Okay, so what you are left with is an advection of momentum in the x1 direction balanced against diffusion of momentum in the x2 direction. Okay, now the other equation, Stokes, I think it's called the first problem or the second problem, I'm not sure, the impulsively started plate. Okay, moving with the velocity, and we have these velocity profiles like this. And the equation was du1 dt equals nu times d square u1 dx2 square. My question is, take this equation and make certain approximations to make that into that equation. What will you do?
Instead of t, we have x1 by.
So the dimensions will give you the clue. What is x1 over? Suppose we treat this as a constant. Okay, that is, momentum is convected in the x1 direction with a constant velocity. So for example, just throw this term off. Okay? Take this term and treat this as a constant and divide x1 by v1. What will that look like? That will look like a time. Right? So that what it says is if I have this boundary layer, if I put a dot and see how far that dot moves, convex, there is a time, certain time it takes for it to move from point A to point B. In that time, the effect of that motion would have diffused in the other direction to the same extent as that occurred in the impulsively started plate. So I need to make certain assumptions. These are not true, but there is a rough similarity between the two. And this is what we observed in that problem also. What is the momentum diffusion proportional to? Square root of nu, kinematic viscosity. Here also we are saying that the boundary layer thickness is proportional to square root of nu. Okay? And there the time for propagation in the extra direction was proportional to square root of nu. So there is some similarity between these two problems, but this is a more complicated problem because it's nonlinear. The other one was linear. To get that, we need to make certain assumptions. We need to throw one of the terms. We need to assume v1 is a constant. Then we can interpret predominantly it's a convection of momentum in the x1 direction that is balanced against diffusion of momentum in the x2 direction. Okay?
If the length is very small and the fluid is very viscous, will these equations still be valid?
Good question. If the length is very small and the fluid is very viscous, then what would happen is, well, the boundary layer theory assumes that still it's an infinitely long plate.
No way it has mattered that it depends on the viscosity of the fluid.
What do you mean? It does. The kinematic viscosity is this.
No, in the other equation that we got at tilde 1, it's like, I mean, if it is like very small then, and it's a very viscous fluid, then how is this equation going to change? Like, because then we cannot make the assumption that del over L is very small. Because the delta is...
No, we are not making that assumption that U over L is small or large. And we are not saying that V over delta is small or large. We are saying V is small, delta is small. But their ratio is of the same order of magnitude as U over L. U could be large, L could be large. Or U could be small and L could be small. Okay? But that ratio U over L is of the same order of magnitude as V over delta. That's the argument that we are making. So by making L small, it doesn't violate any of the assumptions that we have said. So all the analysis will be valid. In fact, L is the length measured from the leading edge. And when you say L is small, it's not as if the plate ends there. This analysis assumes that the plate goes infinitely long from a starting point. Okay? But the other question of what happens if the viscosity is large is a meaningful one. And what would happen is, what happened? I missed it. So what happens when the viscosity is large, you will get a boundary layer that's like this. Maybe another one that looks like that. Okay? This is nu 1, this is nu 2, that's nu 3. So nu 1 would be nu. Nu 1 will be smaller than nu 2, smaller than nu 3. So the boundary layer thickness varies as square root of nu. As nu increases, the boundary layer thickness increases. So if you take a very short length, for example, compare, you will find the boundary layer thickness for a thicker fluid to be much thicker. Okay, the more viscous fluid to be much thicker. Okay, and you can, if you know it for one, you can predict it for what the other one is at the same length using this relationship. Delta 1 over delta 2 should be equal to square root of nu 1 over nu 2. So if I tell you what the boundary layer thickness is for one fluid, you should be able to calculate it, what it is for the other fluid. Okay? Any other questions? I think we're almost out of time.
In my doubt was like we had made an assumption in the second, in the x2 component, that del over L is very small, so we neglected all the terms. But if the delta is very large and L is small, can you still do that?
As I said, L, when you say L is small, it is never finite. We are considering an semi-infinitely long plate. Okay, so you can ask the question a different way, which would be, the plate is long, but is that assumption valid near the frontal region? Okay, that's a good question. And I need to talk about the nature of the partial differential equation between parabolic, elliptic, and hyperbolic. So what you're saying is, put it in a physical way. For example, I say that the plate starts here. Okay, ask the question as the fluid is coming this way. When the fluid is at a certain distance away from the plate, does the fluid know that the plate is going to be there? The answer turns out to be the answer that you are seeking for your question. Okay, that is, if the viscosity is large, then what we call the elliptic effect, that is the momentum diffusion in the direction of flow, is large if the viscosity is large. That means the fluid that is approaching a plate will already feel the presence of the plate. But if the viscosity is small, it will feel it only when it goes even closer. Okay, so to the boundary layer approximation, this is consistent in the sense that the so-called elliptic effect, that is the momentum diffusion in the x1 direction, is negligible. But in that extreme condition that you put in, near the leading edge, the boundary layer theory will break, because that assumption will break. Okay, that's a good, very perceptive question. Some lectures we get a lot of these questions, some lectures we don't. I wish that every lecture you guys keep asking questions. Okay, so I think we are out of time, so we will continue with the boundary conditions and the Blasey solution. And remember, I'm not telling you which day, but one of those 2 days I will have a quiz. Oh, we never recorded this lecture. I guess I didn't.
Oops. Okay.
Oh, okay. I did. I posted the next assignment, number 6, a week to do. And it's exactly the same problem that we did in class, creeping flow, but over a fluid sphere. So the sphere is also fluid, but you assume it to be maintaining its shape. It's not deforming as the fluid, another fluid is flowing past it. So it's basically an opportunity for you to work through all the mathematical details that we went through in class for a solid sphere, but twice, once for the inner sphere, once for the outer sphere, and then go through the solution for the stream function, for the inner one, outer one, get the stresses on the surface, and show that the drag force is given by this expression, where sigma is the ratio of the viscosities, the two viscosities. So you will notice that as sigma goes to 0, I think sigma, did I define it? Yeah, mu O over mu I. So sigma goes to 0 means that the inner fluid viscosity goes to infinity. That means it's a solid. It's behaving more like a solid. And you get the original result that we saw, 6 pi mu u A. Now if sigma goes to infinity, what does that mean physically, and what happens to that expression? Sigma is a ratio of the outer fluid to inner fluid. Okay, so if sigma goes to infinity, that means the outer fluid viscosity looks much larger than the inner fluid viscosity. So it's as if the inner fluid is a gas bubble, for example. Okay, so its viscosity will be very small. So in that limit, it will go to, I think, the 1 and 1 will cancel when sigma is very large, and you'll get 2 over 3 sigma over sigma. So it will become 2 over 3. So it will go to the limit of 4 pi. And this is called the Smoluchowski result, which was developed by Smolchowski for the first time. So the basic idea is to give you an opportunity to work through all the math details on a problem that looks very similar. Now the second part of this problem is back to solid sphere, but now using COMSOL. Okay, here I'm just testing your ability to build on COMSOL based on what you've already seen. So there are two cases. One is a cylinder, another is a sphere. In both cases, when you're building the geometry, you'll just take a circle and put it there. Now, if you choose the 2D axisymmetric, that circle becomes a sphere. If you just pick 2D, then it becomes a cylinder. Okay, so I want you to solve that for a whole range of Reynolds number, 0.1, 1, and 20, and calculate the drag coefficient in each case and compare it with the analytical result and see how far they agree. And when you go to Reynolds number of about 20, you will already begin to see the wake. And I want you to capture a picture of that and include it in your assignment. Okay, so should be fairly straightforward, but just repeating what we did in the class for the first part. So any questions for me? Okay. We're going to continue with potential flow today. But let me just briefly review what we saw in the last class. That is, we showed that the Stokes solution is not uniformly valid, and you should understand what that concept means, that it's not valid over the entire domain. Okay? It's a better approximation near the sphere than far away from the sphere. And a low Reynolds number flow, the influence of the sphere is felt many, many diameters away from the sphere. We saw that both in the film by G.A. Taylor and an order of magnitude analysis to show that the creeping flow solution is not uniformly valid. Then we saw attempts to extend the validity of the solution beyond a Reynolds number of 0. And here we introduce this idea of a regular perturbation expansion process, how to linearize a nonlinear problem and build a series of linear problems, each one of which can be solved relatively easily compared to the nonlinear problem. And we saw another way of linearization, which is the Ausseen method, which is more ad hoc. The first one has some formal structure to it. The second one is I'm just going to decompose the velocity into a main velocity u under perturbation and ignore all the perturbations around it. And he was able to derive and solve the Stokes, the extension of the Stokes problem to get a correction to the Stokes flow. And then we saw what is a Stokes paradox. Does anybody remember what a Stokes paradox is? Non-existent, exactly. Okay. So in the final exam, make sure that some of these concepts you're able to explain in simple words. I'll put the first question is just checking simple answers like that. What do we mean by a Stokes paradox? What do we mean by D'Alembert's paradox and things, stuff like that. And then we started looking at ideal fluids. The Euler equation is an important one, which is a subset of the Navier-Stokes equation where we have the continuity and the momentum equation. But in the momentum equation, we have assumed the viscosity of the fluid to be 0. Ideal fluid, so there is no viscosity, there is no viscous resistance to it. So the only forces that will balance are inertia, pressure, and gravity. And that is what gives rise to the Bernoulli equation. And we saw a Kelvin's theorem which states that in an ideal fluid, the condition of irrotationality is always satisfied. That means the vorticity is 0. That is, if you set an ideal fluid in motion, you can never stop it, but you can never get it to move unless you apply only normal stresses, because tangential stresses cannot cause the fluid to move in that idealization. There are no real fluids that obey that kind of a behavior. But the solution to the Euler equation gives us reasonably good pressure distributions from which we can calculate lift forces in aerodynamic designs, for example. The reason it is called the potential flow, we saw, is because I can define the velocity as a gradient of a potential function. So we have seen stream function before, we have seen vorticity before. We are now introducing a new function called the velocity potential. So it's some scalar function of three-dimensional space, and the gradient of which gives the velocity. And it automatically satisfies the condition of irrotationality by that identity that you see here, del cross del phi equal to 0. But we still need to satisfy the continuity equation. So this will satisfy the momentum equation, the condition of irrotationality coupled with definition of the velocity through the gradient of a potential function will automatically satisfy the momentum equation for us. The momentum equation without the viscous term, the Euler equation. But we still need to satisfy the continuity equation, so we take that definition, put it in there, del dot v, so del dot phi, which is del square phi. So now we get a handle on how to get that function phi. Here we just introduce that function phi as some scalar function, the gradient of which gives the velocity. But how do I get that function? We deferred that question, and now we see if we satisfy the Laplace equation, any function that satisfies the Laplace equation will automatically give you the velocity field through its gradient and will automatically satisfy the condition of irrotationality, so you have a solution. So once again, we are able to reduce the potential wave problem, 3 momentum equation and the continuity equation, to solving a single equation, a single linear equation, luckily for us, that will give us the velocity profile. Once, of course, we get the velocity profile through the definition, we can take the velocity profile and plug it in there, and we can calculate the pressure profile out. We need to get the velocity profile and pressure profile. Remember, these are the 4 variables, 3 velocity components and pressure. So we can get the pressure profile from the momentum equation. And we saw that if we take the Euler equation and dot it with the velocity vector, v dot a force term, that is your energy term or the work term. So that gives us the condition that because of the condition of irrotationality, this is equal to 0. So the meaning of del v dot del is following the motion of a fluid particle in a Lagrangian frame. Whatever that appears in this parenthesis is conserved because its gradient is 0, it doesn't change along that line. So that gives us the interpretation that along a streamline, this quantity in the parenthesis is a constant, so that its derivative is 0. And that is how we are able to integrate the momentum equation analytically and get the Bernoulli equation. So Bernoulli equation is valid only for ideal fluids. Okay? And then we empirically modify it by adding a friction term, a work term, etc. In an undergraduate fluid mechanics course. Now I want to focus attention on 2-dimensional potential flows. Basically, my goal is not to solve differential equations, because solving differential equations is time-consuming and difficult part. Okay, so we always, if we have a PDE, we use separation of variables, we use similarity transformations to get it into an ODE, because I know how to solve ODEs. Okay, so in the same way, what I'm going to do now is devise a procedure whereby I take algebraic expressions, and I know those algebraic expressions are solutions to some potential flow problem. And so I invert the problem, ask the question, for what geometry would this function, analytical expression, algebraic expression that I have, be a solution to the potential flow equation? So I'm going to invert the process. But the logic to do that requires us to use complex variables. Anybody who has not seen complex variables at all? All of you have seen it, right? So we'll go through it very quickly so that you recall what you have seen, and then we will use that to develop the solution procedure for 2-dimensional potential flows. Remember, the moment I say 2D, the thing that should strike you is you can immediately introduce a stream function. Definition for a stream function, which automatically satisfies the continuity equation. Okay, so here V1 is d psi dx2, and V2 is minus d psi dx1. It's exactly the same as the one we saw for the previous problem in Kriving flow regime 2, because it's just a definition of a stream function that automatically satisfies the continuity equation. So by potential function, I found out the Laplace equation will satisfy both continuity and momentum, Euler equation. I want to see whether I can do the same thing from stream function. So if I define the stream function, this automatically takes care of the continuity, but I still have to take care of the condition of irrotationality. That is Kelvin's theorem. If I satisfy condition of irrotationality, I've satisfied Kelvin's theorem, I've satisfied the momentum equation, Euler equation. But in 2-dimensional flow, which vorticity component will be 0? Remember, what is the definition for vorticity? Vorticity omega is del cross V. Okay, and when you're expanding it, you're going to expand it something like I, J, K, the three vectors, and then dx, dy, dz, and then u, v, w. That's the expansion of the vorticity vector. Now, in a two-dimensional flow, what we know is that the velocity vector looks like this: v1 as a function of x1, x2, and v2 as a function of x1, x2, and v3 is 0. Right? So under those conditions, if you ask the question, what is the first component of the vorticity vector? How would we get that? Remember, it is d dy of w velocity, and then d dz of v velocity. That's going to be 0. Why is it 0? Because we have the third velocity component w as 0, and when you take the derivative of the second velocity component v with respect to z, the v component is not a function of z. Are you following me? Okay, so that component is 0. What about the second one? J. For this one, I would use this with this, and that with that, cross multiply, right? So the second vorticity component, omega 2, would be d dx of w. W again is 0. Or d dz of u. Again, u is not a function of z. So that vorticity component will also be 0. So in a two-dimensional flow field, the only vorticity component that is not 0 comes from the third one. Okay, that is using these cross products. So when you expand that, this is what you will get. Omega 3, the third vorticity component, is d dx1 of v2 minus d dx2 of v1. Of course, v1 and v2 are not 0. They are functions of both x1 and x2. So that will be not 0. Okay. So condition of irrotationality means the two vorticity components are already 0. I must make the third vorticity component as equal to 0. Okay. So this is the definition for the vorticity of the third component of the vorticity. So I take the definition for v1 and v2 and put it in there. So I get minus d square psi dx1 minus d square psi dx2, which is minus del square psi. That is equal to 0. So what this means is, if I can get a solution to the Laplace equation, once again the Laplace equation, I can call that as my stream function, and by putting it into the definition of the stream function, I can get the v1 and v2 component, and it will automatically satisfy the what? Condition of irrotationality. Right? It will automatically satisfy the omega 3 equal to 0. So I have two ways of solving the potential flow problem. Either by solving del square psi equal to 0 and say psi is my stream function, and it will satisfy the continuity equation, and it will satisfy the condition of irrotationality, and v1 and v2 I obtain through this definition, these defining equations for stream function. Or I can solve a Laplace equation and take its solution to be, interpret its solution to be potential, velocity potential. And then I get the velocity components as gradient of the potential. And I will automatically satisfy the continuity as well as the Euler equation. So there are two alternate ways of getting the solution to the 2D potential flow problem. Any questions on that? Are you understanding the argument, the logic, the idea behind what I'm talking about? Okay, so there are two functions we can define, potential function and stream function. They're both solutions to some Laplace equation. And we have to define the geometry, of course. We have to solve the Laplace equation in some specific geometry. And then we take those and get the velocity field either from the stream function definition or from the velocity potential definition. But the beauty about this is we don't even have to solve the Laplace equation. So solving Laplace equation is solving a partial differential equation, right? You need to use separation of variables, etc. And for complicated geometries, it can be challenging. So what we are going to do is draw on complex variables, the theory of complex variables, which allows us to get solutions in a very simple way. Okay. So remember, the definition for stream function was v1 equals minus d psi dx2 and v2 equals minus d psi dx1. That was the definition. Now the definition for the velocity potential was v1 is equal to d phi dx1, gradient of a potential function, and v2 equals d phi dx2. Okay? Now, since you have seen complex variable, what does this equation remind you of? Those are the Cauchy-Riemann conditions for a complex analytic function. Okay? What does this mean? It means the following. If I have a complex function f of z, complex function will have a real part to that and an imaginary part to that. So I treat phi as the real part of the complex function and psi as the imaginary part of the complex function. So I put I here. That tells me that psi is the imaginary part. And both phi and psi are functions of x1 and x2. And we're dealing only with 2D flows. Okay? And z itself is the variable. So f is a function. That function is a function of z. Z is a variable, but it is a complex variable. It's not a real. So it is defined as x1 plus ix2. Okay? So we say that this function f of z is analytic when this Cauchy-Riemann condition is satisfied. That function f of z is continuous. Function f, which is a function of complex function f, which is a function of complex variable z, is continuous with respect to z. There are no discontinuities in the field. Okay? Then these two conditions must always be satisfied. Okay? There is a real part. If you take the real part derivative with respect to x2, you should get the same thing as the phi with respect to x1. Or if you take psi with respect to x1, it should be minus of phi with respect to x2. And the other thing that we can show is that del dot gradient of phi dot gradient of psi will always be 0. Okay? What does that mean? Well, for a two-dimensional case, gradient of phi is defined as I1 d dx1 of phi, I2 d dx2 of phi. That's the definition, right? The gradient function. Similarly, for psi, it's a gradient of psi. Okay? So I'm taking the dot product between these two. And when I take the dot product, I will get I1 dot I1, which is 1. So that gives me d phi dx1, d psi dx1. If I take I1 with I2, what will I get? 0. As I'm talking, I'm hoping that you will keep thinking in your mind, and when I stop, your thought process should continue, right? Because you're just not listening passively. You should be listening actively. Okay? I1 dot I2 should be 0 because they are perpendicular to each other. Right? I1 and I2 are unit vectors in the x1 and x2 direction. So when I take this product, I'll get 4 numbers, 4 terms, and only I1 dot I1 will be 1, I2 dot I2 will be 1, I1 dot I2 will be 0, and I2 dot I1 will be 0. So I get d phi dx2, d psi dx2. Okay. Now I use the Cauchy-Riemann condition. Okay. So d phi dx1, if you remember, d phi dx1 is the same as d psi dx2. That is, this first term here is the same as d psi dx2. And similarly, d phi dx2 is the same as d psi minus d psi dx1 from the second equation there. Okay. We already established that. This line we already established by simply the definition, because v1 is defined either as gradient of phi, the two blue things that you see, or as d psi dx2, or v2 as minus d psi dx1. Because v1 is the same or v2 is the same, you have two ways of calculating v1 and v2. One is through the potential function, the other one is through the stream function. So using that, you will see that this is equal to 0. What does that tell you? This statement that gradient of phi dot with gradient of psi is always equal to 0. What does that tell you geometrically? They are perpendicular. Which are perpendicular? What are perpendicular? Which two entities are perpendicular? The gradient of psi, what does that tell you? The gradient of psi tells you the direction in which psi is changing the most. Okay, and similarly the gradient of phi tells you the direction in which phi is changing the most. So if I plot a contours of stream functions, for example, These are psi1, psi2, psi3, and then another contours of phi. These are phi1, phi2, and phi3. At every point of intersection, the two vectors that are tangent to this or normal to that, okay, they must be perpendicular to each other. So they actually form a nice coordinate system, orthogonal coordinate system, the stream functions and the potential functions. But the basic geometrical concept that you should take away from this is when gradient of phi dot gradient of psi equal to 0, that means they are orthogonal to each other. Contours of streamlines and contours of potential lines are perpendicular to each other. Okay, any questions? So here I have basically summarized in cylindrical coordinates the equations, okay, the continuity equation, the condition of irrotationality, the vorticity, and the definitions for UR and U theta in cylindrical coordinates. We have already seen that in Cartesian frame, but here I'm summarizing it in cylindrical frame. You should be able to work with both of them. And so we have del square phi equal to 0, del square psi equal to 0. What is the expansion for del square in cylindrical coordinates? Well, here it is, 1 over r d dr r d phi dr plus 1 over r square d square phi d theta square. Okay, so in cylindrical, in Cartesian frame, this would be simply d square phi dx1 square plus d square phi dx2 square equal to 0. Okay, and similarly for this one, d square psi dx1 square plus d square psi dx2 square will be equal to 0. You should be able to work on either one of those coordinates. Now we're going to digress to recall some of the important results from complex variables so that we can use that Cauchy-Riemann condition in solving potential flow problems without having to solve any differential equations. Okay. So what is a complex variable? Complex variable is any variable that has a real part and an imaginary part. Okay. So here I can label this as x and this as y coordinate. So x plus iy represents a point. Okay, so a pair of point I will simply give as xy, where x is measured on the real axis and iy is measured on the imaginary axis. Okay, the modulus of x is the magnitude of that vector. Okay, so sometimes we write it as simply between two parallel bars, as you see here. That is the modulus of a complex variable, which is the magnitude, which is square root of sum of x squared plus y squared. So geometrically it means the length of that particular vector. Okay. The complex conjugate is defined as x minus iy with a over bar. So z bar simply means that it is a complex conjugate of the original one, x plus iy. Okay, so z bar, the product of that is equal to the square of the magnitude of the vector. In polar coordinates, that is in cylindrical coordinates, all you have to do is apply the coordinate transformation. X is equal to r cos theta, y is equal to r sin theta. So you replace x and y by r cos theta plus I sin theta, and r you can take as a factor, and cos theta plus I sin theta. What is that? That is e to the power I theta. This is another result that you need to recall. Okay, we will use that quite often. E to the power I theta is the same as cos theta plus I sin theta. It's called the Euler's formula. Okay, now we're just introduced what a complex variable is. Okay, how to represent complex variables. It has a real part and an imaginary part. And z is a complex variable. It is written as x plus iy. Now we're going to talk about complex functions. Complex function is a function. What is a function? Just a mapping from one variable to another variable. Okay, so here the variable, the independent variable is a z, which is a complex variable, and f is the rule that maps a point in the xy space to another point in the real and imaginary part of the complex function. So the function itself is also going to be complex. For example, if I take z to the power n, z is a complex variable, z to the power n is a function. So I can replace this by x plus iy, and then, or I can replace this by r cos theta plus I sin theta. I can do this in either Cartesian frame or in cylindrical frame. and using the another identity, cos theta plus I sin theta to the power n is cos n theta plus I sin n theta. If you're doing the expansion of x plus iy, it has to be a binomial expansion, okay, to the power n. So that is an example of a complex function, z to the power n. We'll come back and use that later on, n equal to 2, n equal to 3, n equal to 4, etc. Another example is e to the power z. So z still is a complex variable, but e to the power z is an exponential function. And the definition for that is the same series expansion, z to the power n over n. But this is z square, z cube, etc. So you need to substitute wherever you have a z, x plus iy, if you want to separate the real and imaginary part, which we will always want to do. Why? Because in a potential flows, x and y are going to be the two coordinate systems, and the real and imaginary part of a complex function is going to be your stream function and velocity potential. Okay, so we're going to make that connection, and then we just have to examine various types of complex variables. Now, this idea of an analytic function. What is an analytic function? A function is said to be analytic if it has unique derivative. So that when you're taking the derivative of the function, it must be unique, independent of which direction you are approaching that derivative, in the x direction or the y direction. Okay, so we're going to say the real and imaginary part of that function be u and v. We have been calling it so far psi and phi in potential flow theory, but this is just complex variables. So u and v are two complex, the real and imaginary part of a complex function. Okay, so f of z is equal to u of xy plus iv of xy. Think of it as simply phi and psi, phi plus I psi, for example. So when I say calculate the derivative of that function f with respect to z, what do I mean? The limit process, right? So the limit delta z going to 0, f of z plus delta z minus f of z divided by delta z. That is how I define the derivative of any function, real function. I am applying the same definition to complex function also. So the meaning for the derivative of this function is I calculate this function in the limit of delta z going to 0. Okay, so the numerator I'm going to call as delta f. That is f calculated at x plus delta z minus f calculated at z. So I call it as delta f. Now delta f is going to be complex, so I'm going to have a variation in u and a variation in v. Similarly, delta z will have delta x plus I delta y, I guess, plus the I there. Right? So I'm decomposing both the numerator and the denominator into its real and imaginary part. Okay, so what I want to do is I can calculate this derivative in a number of ways. For example, let me just, this is xy space, and I have another space where I have u and v. Okay, so for every point z is a point in the xy space. So I take the x value and y value, put it into this function u, and put it into this function v. I calculate u and v. Okay, that gives me a corresponding point in the uv space. So function, as I said, function is a mapping from one space to another space. We are used to the function of a scalar variable f of x. X is one line, and then we plug in the definition for x into f, calculate it, and you get a curve. But here what happens is for every point in the complex plane xy, I will get a corresponding point in the complex function uv. Okay, and the recipe is very clear, because if I tell you what u and v are, you can select a series of xy values, plug it in there, and plot the corresponding one. But what we want to do is evaluate the derivative of this function at a particular point. So I can calculate the derivative either by perturbing in the u direction only or in the v direction only. So the point is, whichever direction I take, I should get the same value for the derivative at a particular point. If the function is analytic, if the function is continuous, the derivative must be unique, no matter how I calculate it. So I do it two ways, and this gives me, when I do it two ways and insisting that they must be the same, gives me the Cauchy-Riemann condition. So the Cauchy-Riemann condition is no magic, it simply falls out of this condition that the function must be analytic. Okay, so follow this logic. So I'm parallel to x-axis, delta y is 0. There is no variation in the y direction, in the perpendicular vertical direction. So I'm considering only variation in the x direction. Okay, so this formula will become u plus I delta v in the numerator, but in the denominator, since I have already set delta y equal to 0, I have only variation in delta x that is possible. Okay, and so in the limit of delta x going to 0, this becomes partial of u with respect to x plus I times partial of v with respect to x. Follow this carefully, okay? Or do you understand what has happened here? I've calculated the derivative d of dz, but in a way where I've specified delta y is equal to 0. That means I've set this equal to 0. Okay? So denominator I have only delta x. Then delta u over delta x in the limit of delta x equal to 0 is du dx. Plus I times delta u over delta x, delta v over delta x as delta x equal to 0 is dv dx. Okay? That's basically applying the limit, the definition of a limit. Next, I do fix the delta x as equal to 0. So I'm varying delta y. I'm calculating the derivative approaching that point, the same point. The derivative is evaluated at the same point, but approaching in the y direction. Okay, there is no variation in the x direction. Then I will get I delta y in the denominator. Okay, and so I get limit of delta y going to 0, delta u over delta y, that is du dy. Now, why did I put a minus I here? 1 over I, right? So 1 over I, so I just multiply and divide by I. So it becomes I square is minus 1. So I'm left with an I in the numerator. Okay, the next term, both the i's will cancel out. So that will give me the real part, dv dy. So now I insist that this derivative and this derivative must be the same because I'm calculating the derivative at the same point, just two different ways. And that means the real part in here must be the same and the imaginary part in here must be the same. So du dx must be equal to dv dy and dv dx is equal to minus du dy. And that is the Cauchy-Riemann condition. Okay? So, to summarize then, if you are solving the Laplace equation, okay, the Cauchy-Riemann condition will also mean that they automatically satisfy the Laplace equation. So if you have two variables that satisfy the Laplace equation, then they will give you, the real part will give you the psi, and the imaginary part, the real part will give you the phi, the imaginary part will give you the psi. So you don't really need to solve any differential equation. You can take a complex variable, and that complex variable function is going to be a solution to some potential flow problem because it will satisfy all the sets of conditions, continuity equation, Euler equation, and the Cauchy-Riemann condition. That is the connection between complex variables and potential flow. Any questions on that? Okay. So to summarize, take any complex function that is analytic, that means it has continuous derivatives, no discontinuities in the function, separate it into real and imaginary part. The real part will give you the potential function. The imaginary part will give you the stream function. And they will satisfy the Cauchy-Riemann condition, they will satisfy the Laplace equation, they will satisfy the Euler equation, continuity equation, everything. Now, one more thing to notice is if I take such a function that is given a function f of z, if I take its derivative with respect to z, okay, and look at the derivative of the function, its real part will be v1 and its imaginary part will automatically be v2. So this is called the complex velocity. The velocity is not complex, it's a complex variable, but its real and imaginary part gives you the velocity components. And it is simply the derivative of that complex function, analytic function. Okay, that's another result that we will use. That is given, I will give you a function, a complex function, and then say find its velocity field, find its stream function, find its potential, find its pressure distribution from there, etc. We'll do a few examples that will make it clear. So when you're dealing with Cartesian frame, this is fine. Okay, you can take the derivative of this f with respect to x1, and you can get the velocity components. But if you want to do it in polar coordinates, r theta coordinates, cylindrical coordinates, then what you need to do is use the transformation, the v1 equals vr cos theta minus v theta sin theta, coordinate transformation, and v2 equals vr sin theta plus v theta cos theta. Okay, but we know that df dz is given as v1 minus v2. Okay, so take this v1 and plug it in there, and take that v2 and plug it in there. Okay, so v1 becomes vr cos theta minus v theta sin theta, and v2 is this. And combine them, that is, take vr as a common factor from both, and then v theta as a common factor from both terms, and you'll get cos theta minus I sin theta in both terms, and that is nothing but e to the power minus I theta. Cos theta minus I theta, minus I sin theta is. So what this tells us is, if I take the derivative of that function f that I give you, and then extract this factor, and this is key, okay, extract this factor e to the power minus I theta, whatever is left, split it into its real and imaginary part, and its real part will automatically give you the velocity component in radial coordinates, and its imaginary part will give you the velocity component in the theta direction, in the cylindrical coordinates. Okay?
So, will you say automatically?
Yeah, automatically meaning the interpretation for those would be that its real part is VR and its imaginary part is V theta. So the procedure that we are going to do for solving for solving potential wave problems is take some complex function and do the analysis. So in the first example, I'm giving you the complex function is f is equal to uz. U is a constant, a real constant. Z is a complex variable. Analyze for what problem that could be a potential flow solution. That's how the problem will be stated in an exam. Okay, I give you a complex function and then say, analyze for what problem, for what geometry this could represent a potential flow solution. And the procedure that you would do is basically the following that we are going to do. So we'll use the definition for z, which is x1 plus ix2. So f of z is u times x1 plus ix2. Now I can separate this into the real part and an imaginary part, ux1 plus I times ux2. So the real part gives me what? The real part gives me phi, the stream function. For the function f, the analytic function, I separate the function into its real and imaginary part. The real part gives me phi, and the imaginary part gives me psi. So I already know what is the potential for this particular problem. The velocity potential is u times x1. What is the stream function? The stream function is u times x2. How do I know that? Because you told me that the function is uz. So I simply separated that. I substituted for x, z, in terms of x1 by x2. I separated the real and imaginary part. So the real part is my phi and the imaginary part is my psi. Okay? Now, how do I get velocity, v1 and v2? Well, I could use either the definition for phi. So I take phi and take its derivative with respect to x1. What is the derivative of ux1 with respect to x1? U itself, right? So here I'm substituting for phi ux1. U is a constant. So dx1 with this dx1 will be just 1. Okay? Or I can take psi and put it into its definition. So v1 would be d psi dx2. That's the definition. But psi is ux2. So when I take the derivative of that with respect to x2, I still get u. So whether I use phi, the velocity potential, or psi, the stream function, I get the same velocity. Of course, it must be true because Cauchy-Riemann condition is true, right? So v1 is the same expression u. What is v2? v2 from the definition for the potential function is d phi dx2. But is phi a function of x2? Phi is not a function of x2, right? Phi is a function only of x1, you see here. So it is 0. Similarly, I can take psi and put that into this definition to calculate the same v2. v2 is minus d psi dx1, but psi is not a function of x1, so that is 0. So we already know what phi is, what psi is, what v1 is, what v2 is. At this stage, you start sketching out what could this velocity field look like. How would it look like? This is x1, that is x2. So v1 is u, right? So it is pointing in this direction. The velocity is pointing only in the x1 direction. There is no velocity component in the x2 direction. The velocity is just u everywhere, constant. Okay, I should actually draw the same vector length everywhere. So it is a uniform flow. A uniform flow in the x1 direction. Okay, so suppose I put a plate here. Will it affect the velocity field? I put a plate there. What would happen? What would happen in reality and what would happen for an ideal fluid? In reality, there will be a boundary layer because the fluid must stick to the plate. The plate is not moving. But ideal fluid will simply slip past it. So you would not, the ideal fluid will not even notice the presence of a wall there. Okay, so you could take any of the streamlines, and these are all streamlines, right? This is the velocity vector, but that's also the streamline. How do you know? Because what is streamline? Stream function, psi u times x2. Okay, so if I, for example, what would this streamline be? Psi is equal to 0 because x2 is 0. This is the origin. And if x2 is 1, then this will be psi is equal to 1. If there is 2, then this will be psi equal to 2, etc. Because psi is simply u times x2. I guess I should put 1u and 2u, etc. Okay, so any of those streamlines could be a boundary, and the ideal fluid will not know its presence at all. It will just slip past. Okay. Well, there is another way of getting the velocity, and that is through the complex velocity. Given df, given f, I can take its derivative. Remember, f is given as u times z. If I take its derivative df dz, what will it be? U, right? But that must equal v1 minus iv2, because that is how complex velocity is defined. The derivative of that function is your complex velocity. So the real part of u will give you v1, and the imaginary part of that expression will give you v2. So you can see v1 is simply, because there's only real part, there is no imaginary part. So v2 is equal to 0, v1 is equal to u. Okay, so I said let's sketch the plot, and here I'm showing how to do it with Maple. So you enter the command once you start Maple with plots, and it will spit out all these statements, and then you say contour plot. Contour plot of 2y. I'm plotting the contours of stream functions. Stream function is ux2. So I'm picking u as equal to 2, and x2 is the same as y. Okay, so I'm saying plot me the contours of 2y over a range of x from 0 to 0.5, 0 to 5, and y from 0 to 5. Okay, and that will generate the contour plot. We have already talked about how to generate contour plot if you have to do it by yourself. So that is a graph that it gives. So all the streamlines are horizontal. The velocity vector is along the same direction as the stream function. Okay, so these will be the stream function values: psi1, psi2, psi3, etc. These are contours, and those are the velocity direction of the velocity vectors. So the function f is equal to uz gives you uniform potential flow in the x1 direction. That is the interpretation that we give. We have never solved any differential equation, okay? Because this function will automatically satisfy all the conditions that needs to be satisfied. Okay, it will satisfy the Laplace equations, it will satisfy the continuity and momentum equation, etc. Any questions on that? This is too trivial an example, so you may not really fully appreciate the power of this. But if you want to calculate the pressure, what do? Once you know the velocity field, you put it into the Bernoulli equation, because Bernoulli equation is the integrated form of the Euler equation. Okay, so once you know the velocity, we'll plug it in here, and you can calculate what the pressure field is. Okay, of course, G is a gravitational field that is known, so you can calculate what the pressure field is. Next example, slightly more complicated example. This time the analytic function is given as f of z equals u e to the power minus I alpha z. Here, u and alpha are both real constants. Alpha is a constant, u is a constant. We don't know what those constants mean yet. We need to do the analysis and then give it a physical meaning, attach a physical meaning to each one of those constants appearing in that expression. So right now it's just a complex expression, complex function. It is still a linear function in Z. Okay? So the process is the same. Separate it to get the real and imaginary part, to get phi and psi. Then take the derivative, separate it to get the u and v, u1, v1. Okay? Or you can take the derivatives of the stream function and velocity potential, any method that works. There are three methods of getting the velocity components: from the complex potential or from phi and psi by using it in the defining equations for phi and psi. But the first thing that we need to do is expand it. So u e to the power I z is u times cos alpha minus I sin alpha. Again, these formula you don't have to remember. I put them in the formula sheet for complex variables, the relationship, something like e to the power I alpha. You don't have to remember. Just use, it's in the formula sheet, cos alpha minus I sin alpha. Of course, z is equal to x1 plus ix2. Okay, so we have now a complex product of two complex expressions. Okay, so you need to take the product and separate them into real and imaginary part. So when you do that, for example, u times cos alpha times x1, okay, cos alpha and x1 cos alpha, that's a real part. And then when you do I sin alpha and ix2, what will you get? I squared sin alpha x2, but I squared is minus 1. So that's also real. That's where you get this, x2 and sin alpha. And when you take cos alpha with ix2, you get a part of an imaginary part, right? So there will be x2 cos alpha, x2 cos alpha. Okay, and when you do, which one is that? I sin alpha with x1. That will also be imaginary. Okay, that gives you x1 I sin alpha. So there are four terms, but they are regrouped. So one grouping the real part, the other one grouping the imaginary part. So the real part gives you phi. So the phi is going to be this part. Okay, and the imaginary part gives you the stream function. Now you can map, you can contour it. You can go to Maple and then ask it to plot. What do you think? Let me ask you to imagine, and how will the stream functions, and maybe you should get the velocity field first. That might help. So to get the velocity field, as I said, you have a number of options. One is using the definition, d phi dx1. v1 is d phi dx1. I already know what phi is. So when I put that and take the partial derivative, I'm going to get u cos alpha. x2 is the derivative will be 0. Similarly, v2 will be u sin alpha. And you can get the same thing by taking f df dz, okay, which simply leaves you with u e to the power minus I alpha, which is u cos alpha minus I sin alpha. So the real part gives you u, the imaginary part gives you the v1 and v2 components. Am I going fast? Are you guys following me? If I'm going fast, you need to slow me down. Okay, so now with that information, how does the velocity field look on an x1, x2 coordinate or xy coordinate? And what is the interpretation for u and what is the interpretation for alpha? Both are constant numbers. So fix alpha as a number. How would the velocity field look? Here I'm going showing with an example. Okay, alpha is 45 and u is 1. So the stream function is minus x sine alpha, which is you see here, plus y cos alpha, which you see here. And then I'm saying plot it for x between 0 and 5 and y between 0 and 5. And you can see the graph and ask, does it make sense? What are these? These are contours of stream function, right? So this would be psi 1, psi 2, psi 3, etc. because that's what I'm plotting. So that means that the velocity vectors are all pointing in this direction. So what would be the x1 component? And what would be the meaning for alpha? If this is alpha, then the x1 component will be u cos alpha. Next two component will be u sin alpha. Okay. So from that you know that this also represents uniform flow, but not in the x-axis, not in the y-axis, but at an angle alpha. So alpha is the, you now give the meaning to this parameter alpha in the expression that was given to you. So you are given that f is equal to u e to the power minus I alpha z, and asked for what potential flow geometry is that a solution? And the answer is, it is a free stream velocity with a constant velocity u and a constant angle alpha to the x-axis. Okay. Any questions on that? Example 3. Now what we are doing is we are considering a nonlinear function, z to the power n, not z, but z to the power n. N could be greater than or equal to 1. It could also be equal to 1. So when it is equal to 1, you should get the previous result that we get. Now the question is, what is the meaning of u and what is the meaning of n? We don't know to begin with. You need to analyze the problem and then put a geometry around it to see for what geometry, what does the flow field look like. Okay. So here I'm going to do this in cylindrical frame. So I'm going to use that z is equal to r e to the power I theta. Why? Because otherwise I have to do a binomial expansion in x1, y, or x1 and x2. Okay. Here I can use the De Moivre's theorem to relate e to the power I theta to cos theta plus I sin theta. So it is r to the power n cos n theta plus I sin n theta. And so the real part is u r to the power n cos n theta, and the imaginary part is u r to the power n sin n theta. So once again, very easy to separate the velocity potential and the streamlines, the stream function. They will satisfy the Laplace equations, you can verify that, and they will satisfy the condition of irrotationality and the condition of continuity. Now we have to interpret what does it mean. Okay, so one way of doing that, typical way of doing that is map out some streamlines to sketch it out. For example, when does the streamline equal to 0? In this expression, when n is equal to 0, sine 0 is 0, right? So that could represent a streamline. Okay, and similarly, whenever n is equal to pi, theta here is equal to pi over n. Okay, this theta is equal to pi over n. The n and n will cancel out. Sine pi is also 0. Okay, so that line will turn out to be a line like this with an angle of pi over n. So you can now give it meaning to the value of n. What is n? N is certain angle sector that is swept by it, where the streamline could again become 0. Okay, so it turns out that this particular function represents flow past wedged sectors. So if you have a plate like this and another plate like that, and you have a flow, the streamlines could be something like this. Okay, and so this angle could be changed. You could have, for example, this angle being 90 degrees. Then you will have streamlines like this. And that will be your stagnation flow, a flow that impinges on a plate and is deflected. Okay, so to get the process for the velocity field, it's basically the same. You have three choices: either use psi in the definition, or use phi in the definition, or take the derivative of f with respect to z, which is n u z to the power n minus 1, and remember, you must extract e to the power minus I theta. And whatever is left, split it into its real and imaginary part. The real part gives you UR, the imaginary part gives you U theta. So here you are putting Z to the power n minus 1, which is I to the power I n minus 1 theta. And of course R to the power n minus 1. All we are doing is substituting Z equals R e to the power I theta. Okay? And then you have n u r to the power n minus 1. And what you need to observe carefully is this term has e to the power minus I theta. And then what is left with is e to the power n theta. So we're splitting it into two parts. E to the power minus I theta, which comes from this minus I theta. And then e to the power I n theta, which is this part. Okay? R to the power n minus 1 stays as it is. So we have extracted e to the power minus I theta. Whatever is left, you split it into its real and imaginary part. And that will give you VR and V theta directly. Okay? So we have extracted e to the power minus I theta. And whatever is left, you split it into the real and imaginary part. I think once again I have a typo there. Let's see. This is not a deliberate typo, but who can catch what the error is? There is a typo somewhere there. E to the power I n theta is what? Cos n theta plus I sin n theta. So there must be an I there. Okay? And then the real part is cos n theta. Cos n theta times n u r to the power n minus 1. And the imaginary part is sin n theta. That gives you V theta. Okay, so you get VR and V theta. Do you get an idea on how to solve potential flow problems now or not? Yeah.
Why the streamlines like that?
Yeah, I probably jumped a bit ahead and showed you that the streamlines look like this. But the way that you get that is only by plotting the contour. Okay, you have to go to Maple and plot it, or in your mind do this thought process, that is, fix the value for psi here, fix the value for theta, and solve for r, and set a series of points, and then you have to connect them. With a calculator, you have to do that. Or you have to go to Maple and put that one. So you need to actually map out this function to see that it is like this. So all I can show from this expression is at these two values of theta, stream function is 0. So these two are legitimate streamlines. Okay, and the other streamlines are non-zero values of streamlines. But the next part here, we actually show how does the velocity field look like. Why does I put an arrow like this? Is that arrow right? Why does the velocity go into the sector one end and come out of the sector at the other end? You can get all those by looking at this. For example, sine n theta is positive for theta between 0 and pi over n. So V theta is negative. Okay, V theta is negative means you must have a V theta component in this direction because I'm measuring theta in that direction, positive. Okay, and similarly, cos n theta is positive for theta between 0 and pi over 2n. So VR is positive. Okay, and from pi over 2n to pi over n, VR is negative. So VR positive means it's going out. VR negative means it is coming in. Okay, so I'm dividing this into two segments, pi over 2n and pi over 2n to pi over n. Right? And in one segment I'm showing VR is negative, in the other segment I'm showing VR is positive. That tells us that the streamlines must have this kind of a flow behavior, coming in one and going out. And V theta is always negative in that quadrant. If you go to the other quadrant and do the same analysis, you'll get a very similar pattern that is consistent with this. Okay, so that kind of an argument is the one that establishes what the flow directions are. Even if you ask Maple to plot the streamlines, it's just going to give you the set of curves, but you don't know which the direction of the flow. So you need to go through this to figure out what are the directions of the flow. Okay, here how to plot the contours in Cartesian, in cylindrical coordinates. So you need to specify coordinate is cylindrical, and then give the expression and the range in r and in theta. So this is for selection of a particular value of n, which is the stagnation flow. So in this case, what happens is that it is as if the liquid is impinging and then diverting. Okay, so you could have a plate here. What would be the velocity on this plate? We can calculate that. It won't be 0. Okay, in fact, if you go to the expression for Vr and V theta, when r is equal to 0, that is at the center, right? You will find at that particular point, it's a stagnation point. Both velocities will be 0, okay? But at any other value, and in fact, you can do only for this geometry in Cartesian frame also. Any other sector, any other angle, it's best to do it in cylindrical coordinates. For this one, Cartesian and cylindrical will work the same, okay? And you will find that this velocity is 0. Both velocity components are 0 at that point. So that point is called a stagnation point. And such flows are called stagnation flows. Okay? And of course, the velocity will increase, slip on the plate. If you put a plate, you'll still have a slip velocity right on that in the potential flow. And this, I think, is just the potential function, stream function and potential function. And in the book by Kundu, I think Bernstein and Lightfoot don't spend a lot of time on potential flows. Just a few examples. But in Kundu, they have the sketch for various angles. Alpha equals pi over 3, alpha equals pi over 2, 2 pi over 3, etc. So all this classes of entire class of flows past sectors, whether it is obtuse or acute, you can calculate the potential flow from that single solution that we have, single function that we have, z to the power n. What is this one? Okay, well, alpha is equal to, alpha is the angle. Okay, this is equal to pi over 3, pi over 2. So this would be 2 pi. Okay, so it is as if you have a plate, and so the fluid is coming from here and going around that plate. So that would be your streamline. Now remember, these are your potential lines. Potential lines and streamlines should always be perpendicular to each other. That's what it's showing here. All the dotted lines are potential lines, all the solid lines are streamlines. Okay, stagnation flow is a special case when n is equal to 2. Okay, and that is the flow where you have an object like this, a geometry like this. So then z is equal to 2. So in this function, f is equal to u z to the power n, you put n equal to 2, so z squared. Okay, and so for that particular case, phi becomes u r squared cos 2 theta, which you can also translate into Cartesian frame, which will be x squared minus y squared. Similarly, psi, from the previous expression we have, put n equal to 2, you'll get u r squared sine 2 theta, which you can use trigonometric identity to write it as 2 sine theta cos theta, which you can write as 2u times xy. Okay, and similarly for u1, you can get it in one of 3 ways. Either you take the psi, put it in its definition, or take phi, put it in its definition, or take the derivative. Okay, when you take the derivative, it is 2uz, because it is a z squared, it becomes 2uz, and z write z as x plus iy. So you get 2ux for u1 minus 2uy for u2. Okay, and at x1 equal to 0, x2 equal to 0, or xy equal to 0, both the velocity components are 0. That's your stagnation point. Once you have obtained these two velocities, v1 and v2, you can get the pressure, as I said, from the Bernoulli equation. So in this particular case, all it is P equals P0 minus 2 rho u square x square plus y square. How did I get that? I simply substituted for v1 and v2. Take the dot product. So it's simply v1 square plus v2 square. that is 2u square x square plus 2u square y square. So I take 2u square constant out and I get x square plus y square. P0 is some reference pressure, okay, because this must be constant. So I don't know where the constant is. So I evaluate the constant by putting x equal to 0, y equal to 0, call that as P0. So P0 would be this pressure, stagnation pressure. So if I know the stagnation pressure, I can calculate the pressure field at any other point from the Bernoulli equation after I obtain V1 and V2. Here I have a question for you to think about. The statement I make is that the above solution not only satisfies the Euler equation. We know that these velocity fields, the pressure fields, if I take them and put it into the Euler equation, it will satisfy that. Okay. It turns out that they will not only satisfy the Euler equation, but they will satisfy the complete Navier-Stokes equation, including the viscous term, that is, including this term. You can take these velocity fields, plug it in there, and you will find that it is equal to 0. Okay. So the question is, why is Euler solution not a solution to the full Navier-Stokes equation? Do you follow my question? The argument that I'm advancing is any solution to the potential flow problem that I have given so far obviously satisfies the Euler equation, but if you take it and plug it into the Navier-Stokes equation, it will also satisfy the Navier-Stokes equation. So one can argue that all these functions satisfy the Navier-Stokes equation. So then why is it not a solution to the real fluid problem? In fact, I show that if V is given as the gradient of some potential function, I evaluate this term in general for any potential function. Nu times del square V is nu times del square V. V is given as gradient of phi. Okay, so I use the index notation and then I switch the indices out, and then I have d squared phi dxi dxi. But I know that this is automatically 0, right? Every potential function will satisfy the Laplace equation. So this term would identically be equal to 0 for every solution that I have examined so far. That's I claim so far satisfies Euler equation, but now I'm showing that it also satisfies the full Navier-Stokes equation. And the question that I'm asking you is why? I guess the answer is also there, because it does not satisfy the no-slip condition. Every function that we have solved so far for the sectors, for the uniform flow, will also satisfy the full Navier-Stokes equation, even though it was not our intention. Okay, it turns out that because of this definition, it satisfies the Laplace equation. That means the neglected term will automatically be 0. So it will also satisfy the full Navier-Stokes equation, but it will not satisfy the no-slip condition. So these are not full solutions of the real problem. These are still idealized solutions for ideal fluids, fluids that have 0 viscosity. Any questions on that?
Yeah, 0 viscosity.
0 viscosity is what we call an ideal fluid. So there is really no fluid with 0 viscosity, even though people claim that helium, for example, at very, very, very low temperatures, close to absolute 0, behaves in a very strange way as an ideal fluid. It comes closest to the ideal fluid. You can pump it without any friction, that kind of thing. So in that limit, some strange physics happens. Superconductivity occurs in that limit. So in the same way, there are some evidence that they may be acting like an idealized fluid with almost 0 viscosity.
Viscous heating term.
Very slow, viscous?
Viscous heating.
Yeah. Such fluids, if they exist, they don't have any viscous heating because there is no friction, right? But as I said, they don't exist in reality except maybe in that extreme limit. And so this is an idealization. And the key point I want to drive here is that all the potential flow solutions will satisfy the full Navier-Stokes equation, but they don't satisfy the no-slip condition, so they are not real solutions to real fluids. Okay, so that's where the boundary layer theory will come and help us resolve that conflict. Okay, let's do one last example very quickly, and then I have a number of examples that I'm not going to go through in the class, but I put it in the notes and as a reading assignment. So I want you to go through that and understand what each function is. Basically, there is no limit to it. There is a whole book devoted to complex variables that takes different complex variables and analyzes for what geometry it would be a solution. Okay, so here we are taking, now because these equations del square psi and del square phi equal to 0 are linear, what that means is if I have a number of different solutions, I can add them up, I can superpose, and the superposed solution, the added solution, will also satisfy these equations. Linearity allows you to superpose the solutions. So I have analyzed one function already, which is u times z. Now I'm analyzing a different function, a square over z, and I'm adding them up in fact. So the function I want to analyze is f of z is equal to u times z plus a square over z. For what geometry is that a potential flow solution? That is the question. Okay, and here u is a constant and a is a constant. What is the meaning for a? What is the meaning for u? We need to discover that after the analysis. The procedure is basically the same. Once again, we are going to use cylindrical coordinates. So wherever you have z, you substitute by r e to the power I theta. So here r to the power minus 1, because z appears in the denominator, e to the power minus I theta. Then do the expansion. The expansion is r cos theta plus I sin theta plus a square times r to the power minus 1, which remains the same. But e to the power minus I theta is r cos theta minus r sin theta. Sorry, there is no r there. R is already, that's another error there. It must have been, that shouldn't exist, because that's simply e to the power minus I theta, which is cos theta minus I sin theta. The next step is collect the real terms and collect the imaginary terms. Okay, so when you collect the real terms, you get u r cos theta. There is u r cos theta plus from the next term a square over r cos theta. Okay, so that is the real term coming from the first one here and thus. Then take the imaginary term I sin theta, and that gives you this u times r minus, here you have the minus sign, and then a square over r sin theta. So the real part gives you phi, and the imaginary part gives you psi. Now you can begin to map. What would the zero streamline look like? When sine 0 is 0, sine 0 is 0. So obviously the line that goes, this is your origin, this could be a streamline, psi equal to 0, right? When, under what other conditions psi would be 0? Sine pi, right? So that could be a streamline. So this entire thing could be a streamline. What are the conditions? What about when r is equal to a for all values of theta? It is 0 too, right? So if I take a for all values of theta, means I can draw that, because that is r equal to a for all values of theta. That's how I get a cylinder. So this represents potential flow past a cylinder if you take only the outside. If you take the inside, you have to give it a different interpretation. It's probably like a flow due to a sink or a source, okay? A sink under source, because whatever it produces inside is sucked up inside itself. So remember, along a stream, across a streamline, there is no velocity, there is no cross flow, because by definition, streamline is one that has tangent velocity vector. Okay, so the fluid that is inside, if there is any fluid that is caught, it cannot go out, and the fluid that is outside cannot go in. And then you can ask the question, what are the other streamlines that I can plot? That's not going to be so obvious. Okay, you need to pick a value of the stream function sine, and pick a value of r and calculate for theta, or pick a value of theta and solve for r and plot those points. And you'll find that the streamlines look like this. These are psi 1, psi 2, etc. So you give this an interpretation that it is the flow, ideal flow, potential flow past a circular cylinder. Now to get the velocity vector, you take the derivative of the string function, this derivative of the analytic function f, which is, remember, the function is z. So the derivative of this z is simply 1. And the second term is a square over z. Derivative of 1 over z is minus 1 over z squared. Okay, and then you still need to separate. And when you're separating it, you need to make sure that you extract e to the power minus I theta. And look at what is left. And split that into its real and imaginary part. And that gives you ur and u theta. So ur is this. And u theta is this. After you have extracted e to the power I theta out. Whatever is remaining, you separate into real and imaginary part. Now you can say, okay, I can put directions, okay, because I can calculate the magnitude of ur, where it is positive and where it is negative, and u theta, where it is positive and where it is negative. Okay. So I said sketch the flow pattern, but I think I guess I left the space for that. But I just given you this flow pattern. That's how it looks like. So it will be like this. Psi equal to 0, this is psi 1, psi 2, etc. Okay. Once you have this velocity field, we have the velocity field, the stream function field, etc. So here are the velocities. So you can take that and put it into Bernoulli equation and get the pressure field. Okay, so this is the Bernoulli equation. So substitute for V dot V, which is going to be V dot V is going to be equal to VR squared plus V theta square. Okay, so we already know VR and V theta. So when you substitute that, you're going to get this expression. Okay, but you need to evaluate this constant. So this P0 is pressure at some stagnation point. Then you can calculate the pressure at any other point from this system, from this function. And you can integrate that pressure to calculate the net force exerted by such a fluid. An interesting thing is, even though we said that there is no shear force, can there be a net force exerted by such a fluid on a particle? The answer in general is yes, because that will be calculated from this pressure distribution. Okay. In this particular case, the irrotational pressure distribution, when you plot this function, turns out to be like this. That's the irrotational flow. The real fluid, but remember, we started saying Euler equation is valid for very large Reynolds number when viscosity is very small. Okay. So if you take a real fluid, and this people have measured it, this is how the real velocity, the pressure field looks like. This is for Reynolds number of 10 to the 5. Okay. So there are differences for bluff objects like this that are round. It agrees reasonably well in the front end, but near the separation zone, it differs quite significantly because there is a separation that is occurring in real fluid. In this potential flow, it doesn't occur. And how do I calculate the force? I calculate the force the same way as before. The stress dotted with K in the direction of the velocity field U. Okay, evaluated at R equal to A on the surface of the cylinder. But Tn here, the stress is nothing but pressure because there is no shear. It's simply minus Np dot K. But I already found out what P is. Okay, so when you calculate this, plug in that expression and evaluate the integral, I get the integral to be equal to 0. Why is that? This is called the D'Alembert's paradox. There is no form drag for flow past a potential flow. That's because if you look at the pressure field, you will notice that it is symmetric. Moreover, the pressure that is applied in the front is the same as the pressure that is applied from the back of the cylinder. So they basically cancel out. But for any other shape of the object, you will find a net pressure, okay, a net force. And in fact, the place where this is used most often is in aerodynamic objects. If I have a plane wing like that and I integrate this pressure distribution around it, I will get a net pressure that is non-zero. And I can get the direction for the net pressure. Okay, and that would be the lift force. If I resolve it in the vertical direction, that will be the lift force. And that prediction is very accurate for these kinds of shapes of objects. But for cylindrical objects like this, as you can see, the error is already large between the actual pressure field and what is calculated from the irrotational flow. Okay, this is the section for self-study. What I've done here is I've given a lot of these complex functions, m over 2 pi log z. Take that, go through the splitting of it into real and imaginary part, VR and V theta, calculate the pressure, and map out for what geometry it is a solution. So I have about 4 or 5 examples that I want you to study on your own. I'm not going to cover those. And in the next lecture, I will start off with all these you need to study by yourself for the final exam. I'm going to start off with boundary layer theory on Thursday. Okay? I will stop there.